I'm going to talk a little bit about authentication of Internet of Things. And basically, if we're talking about authentication between you and a device, the best kind of authentication is mutual authentication, where you authenticate to the device authenticates to you, and everybody knows each other. And so the best way to do that in an Internet of Things fog would be that when the thing talks to you, they're probably going to talk to you maybe with ideally with one using one ECDSA a private key that's at least 128 bits or more. It turns out that I took a look at what bit rate or bit size that hasn't been cracked yet. And the largest Bitcoin key that was cracked was like 112 bits or so. So 128 bits gives you a little bit margin, but if you want to be really safe, you go with 256 bits. And then when then it's the you talking to the thing, where you're trying to prove that it's really you. And my recommendation on that is a little bit different than probably most people, and that is that you use at least 2 ECDSA private keys to sign. And that you have at least 2 or more public keys then in the device to authenticate that signature, and you demand that at least 2 signatures be used. And the reason is that it's, nowadays it's so easy for people to compromise a single device that by requiring multiple keys on the device in order to sort of log into it, you provide a second layer. It's almost like a two-factor. It's the closest thing to two-factor auth that you're going to get. So it provides marginally higher level of security because somebody could have stolen that device that had that private key on it. So it's just a little bit stronger. It depends on the application, though. So, appropriate level of security. But, if you really want to go to the next level, you have three signatures that you have to come up with it from 3 different devices that are verified by the device before you can log into it. The big thing, though, is that the biggest vulnerability there could be some vulnerability at the device side, but probably the biggest vulnerability is going to be when you're logging into the device, your authentication into the device. Because we see all the time on how people's security systems are hacked. And the reason that we read about Walmart and, it's almost like a new security breach every week, is because people today continually use shared secrets for identity and authentication. And we've had cryptography for 20 years. But you find very few people that have switched over to eliminating the use of shared secrets and are moving to something like ECDSA. And you don't want to go to RSA because that's maybe we can talk about that in the Q&A. But you really want to do all your authentication using digital signatures. So all of these things that you see with credit cards or shared secrets, RSA, Secure ID probably should be really renamed RSA Insecure ID. Because any kind of break-in that you have to the other side, it causes a mass breach. And of course, RSA's, the securities were mass breached before, and they can be mass breached again. So I'm going to just go through four myths really fast. So myth number 1 is that a lot of people say, oh, well, we have 2-factor authentication, right? We have username, password, and we have some sort of token, security token, time-based passwords, Google Authenticator, whatever. Those are all based on shared secrets. And so because they are based on shared secrets, you can have a mass compromise, which means you break into the server, you get the secret of the second factor, and you have basically first factor and second factor that's in the hands of an attacker. They can log into your systems. So what you really want to do is eliminate the possibility of a mass breach by using asymmetric crypto. So it means you have a private key on a device that you use to log in. And the second thing, really important, is that people think that when they log into a bank or whatever, and the bank says, oh, well, use this 6-digit number from your RSA secure ID, that must be secure, and that's an independent device, and of course can't be breached. The problem is that the bank can be breached, and the bank has the bank shares a secret with that device. And so if you break into the bank, then you have basically everything you need to be able to log into the bank with a primary key and an out-of-band two-factor. It's not even out-of-band, because the 6 digits you enter is entered into the exact same device as you type in your username and password. So you compromise one device, and your security is lost. Another thing is that biometrics will fix this problem. So you get a new iPhone, right? It's got the thumbprint, and biometrics are the biggest thing. But the thing to be aware of is that biometrics are kind of like a shared unsecret. They're like a password that you can never change, right? Because you can't really change your fingerprints. And so once your fingerprints are known because I left it on my glass somewhere, then that can be used to compromise security, or once it's been compromised and read by one application, then it could probably be injected. And biometrics, when they're done remotely, are particularly troublesome. And the last point is that a lot of people say, oh, passwords are bad. And a lot of people believe, yes, passwords are bad, we should eliminate passwords. But first of all, I'll give you my secret tip for forgetting your passwords, because my wife was forgetting her passwords all the time. And I changed all of her passwords to incorrect, because they would always say your password's incorrect. And this way, she would remember it. And that actually works most of the time. So that's a free tip. But more seriously, passwords are inherently good, because when we talk about 3 factors of authentication, it's something you have, something you know, and something you are. And so if we eliminate passwords, which are something you know, that's actually a bad thing to do. So passwords are actually good. But the problem is that the way we use passwords is wrong. The way that almost everybody uses passwords is that they go and take the password and they hash it down and they send it up, and it's verified at the other end. And that's essentially sharing a secret. And what you really want to do is do it the right way, where the password is combined with a salt on a local machine, and that salt, that combination then is used as an ECDSA private signing key, and then a challenge is coming from the other end to say, hey, sign this. And so the password is just used essentially to unlock, or really combined with the secrets on the device to modify it in such a way that it can then sign that and send it back. And when you do passwords that way, it's extremely safe. Okay, because like I have I started a company, OneID. My password is X for my account. My login is stk@oneid.com. My password is X. It's 1 character. Okay, and I can tell everyone and can be breached everywhere, but nobody can use X to log into my account because they need my device, one of my pre-authorized devices, because X is combined with my devices in order to form a private signing key. So that's actually pretty good, because I was given 10 minutes and I did it in 8.5. So thank you very much.
I'll fix the screen. My last name is Varsanofiev. I asked not to pronounce it for obvious reasons. Everybody calls me Dima. This is easier. It's even consonant, vowel, so it's easy for Japanese. So the topic of the presentation is why is elliptic cryptography good for the fog computing? And it's a pretty straightforward reason. So I would kind of follow up on the previous presentation. Why do we need asymmetric cryptography in general? Why shall we use elliptic curve cryptography in particular for fog computing? Should we use software or hardware implementation? And the net outcome, elliptic cryptography is made for fog. Why do we need to use a public-private key? As was presented in the previous presentation, it's good. And mostly it's good because the fog device is essentially in the hands of an enemy. If you fly a satellite, it costs a lot of money to get to it and extract the secrets. If it's a fork device, it's already in the hands of an enemy. Symmetric keys, one breakout breaks everything. Public-private key, if the public key is lost, nothing is lost at all. If the private key is lost, particular device is lost. Again, not the whole system. Game is not over. The more subtle advantage is that a private key does not need to escape device at all. So you can make a device that generates its own private key and never tells anyone. So never in production, there is a floppy, CD, tape, flash disk, anything that somebody can copy and carry out of your production line and have a copy of your private key. Device can generate the key on its own. So why ECC? Essentially, when we go into a choice of public-private crypto systems, we have two. One is the old RSA, which the banks still use, and the other one is a newer elliptic curve cryptography. Why is elliptic curve better? There are multiple reasons, all very relevant to the devices we're discussing right now. The most important, elliptic curve requires way shorter keys. A typical security for commercial applications is 128 bits of the key. That's the AES key or other symmetric cipher key. If you want to get to the same level of security for RSA, you need to get to about 3,000 bits of the key, which is huge in terms of memory and a lot of time to compute. Because elliptic curve is inherently less breakable, you need about 250, 300 bits of a key for elliptic curve to match the same strength of a cipher. This is good because storage is much smaller, and storage is not cheap if you want a storage from which you cannot dig out the key. You will save also on calculation time. So it's either lower battery consumption or lower power or faster user experience, whatever. That's the reason why NSA has blessed elliptic curve cryptography as part of the Suite B algorithms, which are considered to be good for US government. This is important because that means that unlikely there are major problems there. Unlike the other algorithms which are not blessed, you never know. NSA might know something about them and not share with us, or that means other people also might know something about them and not share with us. Important thing for the fog computing, generating private key with elliptic cryptography is easy. All we need is to get a random number. Essentially, we get a random number, we hide it well, that's our private key. So a device on a production line can be powered up, generate its random number, and just use it as a private key. But that's all manufacturing process. On the other hand, if you took, for example, RSA, private key requires elaborate calculations because it's a private key in RSA is a huge prime number, and the prime numbers are hard to get by. So essentially what you do, you get a long number, pray it's prime, check. If it's not prime, you try next one until you get one. And check is expensive. We all know from our school years that checking for primeness is hard. Software or hardware, if you talk about fog computing, essentially depends on how fast you want it to be and how much power you want to use. On a kind of back of the envelope calculation, if you have 100 megahertz ARM CPU, verification of a 256-bit signature takes about a quarter of a second, give or take, for ECC. You need few kilobytes of ROM. Few can be anywhere from 4 to 20, I would say, in real life. Depends on what do you need to have implemented. Hardware IP core for elliptic curve cryptography for the same curve would take about 16 K gates, ASIC gates, and about 1 kilobit of RAM. And would be, at the same 100 megahertz, would be much faster. Whether it matters or not depends on the application. Hardware implementation by nature is much harder to attack because you know some properties of the CPU to begin with. The attacker knows them as well. They can read the manual. and therefore they can try to figure out what's going on inside by observing from outside. Typical device is hard to open, yes, so you try to observe from outside. And reverse engineering is much harder, and also simply because there is less repetitive stuff happening, the side channel attacks are becoming harder. What's a side channel attack? Side channel attack is a very simple thing. You want to figure what the key is. You can try to open the device and get the key from inside, or you can try to look at how the device behaves and figure out what the key is. For example, if your program computes certain number using the secret key, you can try to figure out that this sequence of events is 0, and this sequence of events is 1 in the key. So you just measure the power of the device, and by subtle changes in the power, you can figure out where the ones are and where zeros are and read out the key. That's a side channel attack. Because hardware consumes much less power and there's much more noise because of it, things getting harder. So in short, if you are planning a design for new gadget, elliptic curve cryptography shall be included. That's pretty much it. Thank you.
My presentation is about React on the edge, so I will be talking more about fog computing and how our platform, PLAT.ONE, does that. So let me start just telling you about our platform, which is a complete end-to-end IoT stack. PLAT.ONE is enterprise grade, so supply high level of scalability, reliability, and security, yet maintaining open interfaces between systems that are to be integrated. PLAT.ONE is cloud ready, so it can be deployed on the cloud, but also on premises, and even embedded in application. It is distributed platform, and we will talk more about these later when we dive into the topic of today. But mainly, we can distribute application and services from the cloud to the edge and federate data gathered and managed by the edge to the cloud. And that is mainly about connecting devices to applications. PLAT.ONE is on the market since 2012, and in 2 years we got about 25 customers using the platform, and among them 3 major telecoms in Europe. And our platform allows and supply our customers to connect their business to the applications. And as you can see, it varies across a different type of sector, looking at the type of customer we have. We can say today that we have a proven technology, ability to execute, and market traction. So now let me say that I'm very proud to say that in the recent months we worked with Cisco on the IoT reference architecture in defining the API for the fog node. And today we will focus on the edge computing, so level 3, which is the important level where data are computed, transformed, queried before to flow to the cloud. More you go up into the stack, less data you have to move. This is the principle. And the importance of data has to be computed by some semantic decision at the edge level. So if data makes business sense, then they can continue and be forwarded to storage and analytics. Otherwise, they are ignored. So how do we see fog computing and how PLAT.ONE support for computing? It's not to replace the cloud, it's to extend the cloud, and extend the cloud for us means to download the cloud services onto the edge, closer to data and where data are generated. solving important issues like concern on latency, fast access to data, and allowing to create an edge network near the devices. Support location-based services to enable mobility, and apply policies for security and privacy issues on sensitive data. So we believe that fog computing is the standard architecture for IoT. So going back to the IoT reference architecture, here is where IT meets OT, operational technology. And I want just to highlight the real-time aspect that is changing between OT and IT. So here we are managing events. We have to react very quickly. Data are in motion. We are not querying databases like in IT scenarios. So we have to be real time. And for doing that, we call that react on the edge. And looking at what PLAT.ONE is able to do is to implement automation control on the fog node. That could be an intelligent gateway, could be an extended box with an infrastructure for deploying different type of services and applications. Automation and closed loop support just to control actuators and react to sensor stimuli as they happen. Ensure low latency and process events as they happen. We have components for data distillation. PLAT.ONE is based on OSGI, so we can move OSGI bundles very easily from one node to the other, from the cloud to the node. And there we can do data compression or other type of data massaging like aggregation, data filtering, data tagging. And so make data more meaningful and apply that semantic decision I mentioned before. And we are able to run analytics on the node. So through continuous query, instead of storing data on the node, we can run queries, multiple queries on multiple data sources in parallel, aggregate queries, apply different type of function like pattern identification, feature extraction, or more simpler statistic functions. And then forward to the cloud what is meaningful. So the result of the analytics or data aggregated and transform into richer information. Then we have, of course, the possibility to deploy application and services on the node. And that is the key factor of our architecture. And to conclude the presentation, I wanted to walk you through a couple of use cases where we have used for two different type of customer this type of deployment. One is a telecom operator. And in their base station, we deploy what is a fog node or an intelligent gateway, where we install our middleware components. This node and this device and this component were integrated with the telco system present in the telco base station for integrating and aggregating data coming from the devices. And for instance, here we partner with several companies, WineAccess in the area of Wi-Fi, low-power Wi-Fi mesh networks, and we work with them quite closely. And the benefits for the operator were to have pre-digested, pre-processed data coming from the devices, contextualized by information gathered from the field, and so the information were more meaningful. And also combined with other parameters taken out from the telco system. The second use case is about parking meters. So we have been looking at what could be a computer in a city. And parking meters are everywhere. And so they are very rich type of appliances with printers inside, HMI, so those characteristics that are typical of a full-fledged computer. And embedding the components that we run on a fog node or on an edge server, as we call it, allow us to link and to use the infrastructure of a parking meter to collect data from various wireless sensor networks around the parking meter itself. So like data from street lights, camera for surveillance, or cameras that were used for analyze the occupancy of spaces in the parking. And there are other use cases where we have used this type of architecture, but that concludes my presentation today. Thank you.
So I'll give you a little bit of background. Z gave his background earlier on Eris, and so I'll give you a little bit of background on us. We're a global company. We're a conglomerate, and our CEO sits over in Italy, Roberto Siagre. He's been a visionary CEO. He's got this perspective he calls it pervasive computing, and this started back in 2007. And if you read that, if you go out on Wikipedia or whatever, what you'll find out is it's essentially fog computing that he was talking about back in 2007. This idea of a tiered effect and edge devices becoming miniaturized and low power and communicating together to create easy communications through every layer and sort of this hierarchical establishment of data going up. In his words, technology, if it's deployed right, should become invisible to us, and that's where he thinks everything's going. So since 2007, and actually a little bit before that, he has been establishing a group of companies. And so what you see here is a group of companies. The Dynatem over on the far right side, that's a high-performance computing company. And so we are known as a company that makes the top 3 supercomputers as far as their power draw and their greenness. So a company of 400 people, globally, we're pretty proud of the fact that we can put the top 3 greenest computers into the market. And so that represents one end of the spectrum from him. He sees all of these different layers, meaning at the data center, supercomputing, all the way down through the middleware, enterprise bus, he calls it, down into the edge devices. The rest of the divisions here, Eurotech Inc. represents Applied Data Systems and ARCOM, and it did represent Parvis, which is mostly military that we divested out of this year. But these have been embedded board computers, so we make single board computers. So we've had this idea of getting embedded intelligence down in the lowest layer since the very beginning. And Advanet does pretty much the same thing over in Japan, but they are a strong brand, and so we keep it. What you don't see here is we have a company called F Labs over in Italy that's just a research and development team. We also own 47% of a company, a Chinese manufacturer over in India. And we also have a company in Italy called F Security that focuses just purely on security. Each one of these divisions has all of their IP, and they bring it together, but then we create a global portfolio by interselling the products between these groups. So we're establishing a full stack, and primarily where that's going is that we feel in order to blow out this 50 billion devices, things have to become easier. We've got to have more standards. We've got to become open. And so we're a company that really believes in open nature. Some people may know the protocol MQTT. That was a protocol that was developed between us and IBM for a project for ConocoPhillips to push SCADA messaging up through satellite systems, so constrained networks. And now it's become a standard. We open source it, it's become a standard, and we've got a history of doing that. The goal is to get people to market shorter, take the complexity out of M2M, create more deterministic development, and reduce their cost and give them a competitive edge. So that's what pretty much everything is about. Now we do that through our own assets, and we also do it through third party. In our assets, like I said, the core of our IoT group, not the supercomputer group, but the IoT group grew out of the embedded board space. And so when we did that, we thought, well, how can we add more value? How can we blow this out? So we took those boards and we stuck them together into systems. And out of those systems, we started creating things like wearable computers, a lot of things that are distributed, full systems that run in buses, embedded systems, and then gateways. We eventually got up in the gateway market. Now what marks this as far as our DNA in that equipment end is we're in the industrial end. So everything we produce is high temp, rugged, industrial, long life. And what we found is that that's kind of niched us out of a lot of the new markets coming into, maybe 80%, 90% of IoT is not maybe in that markets. But as costs come down through, ARM and Intel, we're able to bring those solutions and keep that DNA there to create longer life products. So instead of putting a gateway into a vending machine that is commercial grade and it lasting for 3 years and then pulling it out, we want to put our device in there and have it last 15 years. Now with that, you got to plan for the future. So a lot of what we did from there on out is we said, what can we do from a software level? And we turned to Java as a software protocol, right? And we're one of the few gateway providers that's a full Java stack. And so we created a software stack. It's a software framework, not your typical client that goes on a device, but a full software stack. And that was so that we could actually take a router and turn it into a full-blown gateway and run applications at the edge and control downstream devices and start getting this edge area of the fog starting to communicate together and making business logic. So a lot of the stuff that was talked about earlier. From there, we thought, well, you just put Java on a device and everybody's good to go. And we found out that, no, people aren't good to go. So then we build a middleware application. We call it an integration platform as a service. As a way to try to take that complexity, we feel getting people connected is maybe 60 to 70% of the equations. I've been with Eurotech for 5-6 months actually now. I came from Sprint beforehand. I've got a lot familiar with Z's platform. We worked together over at Sprint, and John's too a little bit. What I saw is a lot of people coming in and playing with this things at the edge and assembling it together and then never really be able to get it to a scalable mechanism and get that messaging up into enterprise applications. And so our goal was to create a middleware platform that takes all of that information and pushes it up and demonstrates it into an enterprise way. And then, of course, we needed to build the professional services around it. In some cases, we've actually taken all those components and packed it together and made full turnkey solutions. We won product of the, I think it's product of the year at M2M Evolution for a ReliaSense product, which is an environmental monitor system that we created just as a prototype to see what we could do with sticking things together, sensors into a box. And what we found out is we came out with a product that actually measures radiation, ozone layers, CO2, and cities are now using that and sticking it on buses and running around their cities and creating a visual representation of the pollution, plumes that are going through their cities. So it's a pretty cool and interesting solution. Again, we're involved in devices that are not nice, right? So we go into helicopters, into ships, into rail, into light rail, into big trucks, into vending machines. So a lot of our systems live outside and we build them to last 15 years. Again, that's a niche on our hardware side. And what we've realized is in order to go out to where we want to, we've got to create a layer, which is our middleware layer. And now our direction is to take third-party equipment and actually start putting it on our devices and enabling third-party gateway providers, and in some cases taking our equipment and putting it on other people's clouds. So we are all about trying to create business relationships between our competitors or so-called competitors. I just put this up as a brag sheet, but there's one important part here. We've got recognition by BDC, by Harvard Research, by Hitachi. We had 22 mentions in cool reports by Gartner, which is one of the most recognized companies within Exida. But I think the more special thing is this year, we took our software stack that we've been working on for a long time. This is our hardware software stack, the thing that makes the gateway intelligent. And we open sourced it under Eclipse. So we took all of that IP, we pushed it out. Now anybody can go out and download that. And since we did that a few weeks back, I've been getting calls from our competition, both on the hardware side and cloud providers, looking at Cura as an open source, free download, get their solutions to be more intelligent. So, and this is just what it is. So this is a hard slide to read, but I didn't want to take you through 13 slides. We sit on top of Java, a JVM, a licensed version of JVM, and we build an OSGI stack. So our idea of this was we looked at the cell phone market, the smartphone market, and we looked at the cell-top box. And we thought IoT should be as easy as that. You should be able to download apps, push new firmware, update things without actually having concerns about the device. And when devices change out, you should be able to take that whole stack and make it portable and drop it into the next piece of equipment, right? And we see a lot of that. We see people start out with one type of equipment, and then as their needs change, they come in with a new type of equipment, and all of a sudden they're re-engineering their entire software stack. So we build it inside of an OSGI container. We put a lot of intelligence in there, including a runtime environment. So it allows you to drop packets right onto that. The fact that we're Java, as it turns out, is really important to a company called Oracle. And so Oracle is looking at this as kind of a breakaway technology. We're one of the few companies that have a complete Java stack. And so they're looking at us as really supporting their requirements going forward. But then as we push in from the application up into the security, we're obviously big believers in MQTT. So we really promote MQTT. It's a great pub-sub environment. It's been talked about several times in this room about decoupling consumers with producers of the data. And by doing that, we also create a security layer. It's not as tight as ECC or anything like that. You know, my belief is security is multiple layers. But what we do is we create this proxy where data is going up, and it's just data. It's blobs out there. Nobody knows where it's coming from. The devices are completely abstracted from the applications. And when people want to write applications, they just write to a common API. They ask, for the information. So an analogy would be in Twitter, we don't, when you tweet something, you don't have to be on a specific device. You just tweet it. The people receiving it don't have to be on specific devices. They just subscribe to hashtag Eurotech and they get that information. And so by doing this, we can take applications, they can just subscribe to our APIs, they can pull that information out. And then we have a whole lot of other things like device management. And when we talk about device management, we don't talk about device management down to a layer where you can manage your router configurations or manage your Wi-Fi signal strength or anything like that. We talk about getting down to a command line prompt and an M device and really representing that device as if it's an IT asset. And for that reason, we've got a lot of recognition from Gartner as being one of the more IT-centric companies in OT because we're trying to represent it up in a way that IT can easily take in this information and integrate it into their enterprise architecture. So in a nutshell, that's what we do. I think that's my last slide. Oh, and I would just say this is just kind of a silly analogy, but what we're trying to be is we're trying to take the complexity out of the middle. And if you think about a vehicle, a lot of power coming out of the engine, we're the gearbox that sits down there where we take all of that power, we scale it down, step it up, whatever it needs to be to the rear wheels so that we can go in the right direction at the right speed. And most OEMs don't go and build their own gearboxes. They go to tier 2s and build that gearbox. So we're focused only in that space. We're not focused in the application or the logistics space. We feel that there's people that are above that layer that are much smarter than us that only focus on that. And what we do is we move data through the internet. So that's what we do. And I think that's it.